The next topic that we'll be talking about is the preparation of buffers. First and foremost, what are buffers? Buffers are systems or acid-base systems that resist drastic changes in pH. Okay, what are buffers made up of? Buffers are made up of weak acids and conjugate bases of the weak acid, or weak bases and the conjugate acid of the weak base. An example of a buffer system is the following. For example, we have weak acid and its conjugate base. Weak acid is, let's say, acetic acid, and its conjugate base, or the salt of its conjugate base. Suppose we have acetate. So the salt of its conjugate base can either be sodium acetate or lithium acetate. We also have other weak acids such as sulfurous acid, and its conjugate base is hydrogen sulfide ion. We have phosphoric acid and dihydrogen phosphate ion. We also have other weak bases and its conjugate acid. Suppose we have ammonia and ammonium is its conjugate acid. We have methylamine and conjugate acid of methylamine. So these buffer systems resist drastic changes in pH for the reason that if, for example, we have a acetic acid and acetate buffer system, if an acid is added to this acetic acid acetate buffer system, then the acid will react to its conjugate base in order to produce the acetic acid. And if a base is added to this buffer system, the base will react to the acetic acid component of this buffer system in order to produce the conjugate base. So whatever is reacted to this buffer system will produce the other component of the buffer system. Why is buffer very relevant in life? Buffer is relevant for the reason that it is one of the physiological systems that maintain homeostasis. For example, when we intake food into our body, that food could either be acidic or basic, but our body pH does not change that much for the reason that there is a buffer system in our body. So that buffer system in our body is made up of bicarbonate and carbonate buffer system. But how are buffers prepared? Before we talk about preparation of buffers, I would like to introduce to you the way to calculate the pH of buffer systems. The first way to calculate it is using the ice table. So suppose we have the following problem below. What is the pH of a buffer system with 1 molar acetic acid and 1.5 molar sodium acetate? The acid dissociation constant of acetic acid is already given, and that is 1.8 times 10 to the negative 5. Okay, we can use the ice table in order to calculate the pH. I have taught you this previously. We have initially 1 molar, and we have 0 molar of hydrogen ion and 1.5 molar of acetate ion from here. So this one is this one, and 1.5 molar sodium acetate is this one. So we don't know what happens during the reaction, so it is minus x molar and plus x molar to the product side. At equilibrium, the concentrations are 1 minus x molar for the acetic acid, x molar for the hydrogen ion, and 1.5 plus x molar for the acetate ion. So we can substitute this equilibrium concentrations to the Ka expression, and we get these values. X plus 1.5 plus x all over 1 minus x is equal to 1 times 1.80 times 10 to the negative 5. The next thing that we have to do is to calculate whether or not x is negligible. But we have calculated this before, and we have found out that x is indeed negligible if our initial concentration is 1. Finally, we can get the value of x, and the value is calculated to be 1.20 times 10 to the negative 5. Getting the negative logarithm of this, because this one is the hydrogen ion concentration as well, so we get a value of 4.92. So negative log of that one, and we get 4.92. The other way to calculate the pH of a buffer system is through the Henderson-Hasselbalch equation. Okay, the Henderson-Hasselbalch equation has this formula: pH is equal to pKa plus log of the conjugate base over the weak acid. So the pKa is given, the negative log of Ka can be calculated directly, and the concentrations of the conjugate base and the weak acid are also provided here. So just plugging everything into this equation and we get the pH value, which is equal to 4.92. So take note that the main assumption for the Henderson-Hasselbalch equation is that X is negligible. Next, we're going to talk about preparation of buffers. So how are buffers prepared? One way to prepare a buffer solution is by adding strong base to weak acid or strong acid to weak base. Okay, suppose we have this problem or example provided here. How much volume of 1 molar sodium hydroxide should be added to 20 ml 1 molar acetic acid solution to make a pH 5 buffer? So we have this equation for that. This is an acid-base equation. So our weak acid is reacted with a strong base, and we produce the sodium acetate salt. Okay, using this IRA table, initially we can calculate the individual moles of each species. So we have 0.02 moles of acetic acid, but we don't know how much moles of sodium hydroxide is provided. So we have, since we don't know the volume of sodium hydroxide, so let's just say that it is X liters multiplied by 1 molar, and we can cancel the unit liter and we get X moles. So the main assumption in order to prepare a buffer using this method is that sodium hydroxide should be the limiting reagent. So therefore we have minus X mole, and plus X mole for the product here. After the reaction, we have this moles of reactants and products. We have 0.02 minus X mole of the reactant, 0 moles for the sodium hydroxide, and X mole for the product. Finally, we can calculate the concentration of the solution by dividing it with the total volume Vt. The unit for Vt is liters, so therefore we got a molarity concentration. So therefore we got a value of 0.02 minus X over Vt for the concentration of the acetic acid after the reaction, and X over Vt molar for the concentration of sodium acetate after the reaction. Then we need to plug in these concentrations to the Henderson-Hasselbalch equation right here, and we have 5 molar here, so we have 5 molar. Our pKa is already calculated, so negative log of the Ka, and we get 4.745. And finally, we need to substitute all these units. This one is concentration of the conjugate base or acetate, so this one is that expression. And this one is the concentration of the weak acid, acetic acid, so we substitute it here. Finally, evaluating this expression would lead us to cancelling the similar units, Vt, and after that we get this expression afterwards. So transpose this over here. So 5 minus 4.745 is 0.255 is equal to log of x over 0.02 minus x. Take the antilog of both sides of the expression and we get to remove the logarithmic function here. And antilog of 0.255 is equal to x over 0.02 minus x. So evaluating this expression, we get antilog of 0.255 is equal to 1.8, and that is equal to x over 0.02 minus x. Finally, evaluating this expression, we can calculate the value of x, which is equal to 0.1286 liters. Therefore, we need to add, converting this to ml, we can calculate that 12.86 ml of sodium hydroxide, the concentration is 1 molar, should be added to 20 ml of 1 molar acetic acid solution to make a pH 5 buffer. This is the first means to prepare a buffer solution. The other way is by mixing solution of a weak acid and solution of its conjugate base, or salt of its conjugate base. Okay, we have this example provided here. How much ml of 1 molar acetic acid and 1.5 molar sodium acetate solutions should be mixed to prepare 100 ml of pH 5 buffer? So from the given question, we know that the total volume of each of these solutions is 100 ml or 0.1 liters. So therefore, volume of acetic acid solution and volume of sodium acetate solution is equal to 0.1 liters. So we know this first equation. So this one is the first fact that we know. So next is we have to make use of the Henderson-Hasselbalch equation since the pH value is provided. So the Henderson-Hasselbalch equation has a pH term here and a pKa value, and we have concentration of each of the species in the buffer system, the conjugate base and the weak acid. So substituting the given in this equation, we have 5 is equal to 4.745. This one is a pKa that is calculated already, plus log of the concentration of acetate ion. So what's the concentration of acetate ion after mixing these two solutions? The concentration of acetate ion would then become 1.5 molar times volume of sodium acetate solution. So if you multiply molar and volume of sodium acetate, then you would get moles, right? Because molarity times volume is mole. So you can cancel liters. So this numerator term is moles of sodium acetate. Divide that by the total volume in liters. So you get a molarity term. So this term is a molarity term. And same with that of the denominator. So you have 1 molar times volume of acetic acid in liters over total volume in liters. So finally, you get a molarity term for the denominator. So this one is molarity of acetic acid, and for this one, it's molarity of acetate in the numerator. So evaluating this expression and canceling all the units that can be cancelled, we get this value. So this one is transposed over here. So 5 minus 4.745 is 0.255 is equal to log of 1.5 volume of sodium acetate over 1 volume of acetic acid. So taking the antilog of both sides, we can get rid of the logarithmic function. And after that, we get a value that is equal to, antilog of 0.255 is equal to 1.80, and that is equal to 1.5 volume of sodium acetate over volume of acetic acid. Finally, evaluating this expression, we get 1.20 volume of acetic acid is equal to volume of sodium acetate. So this one is our equation number 2. Okay, now that we have equation number 2, we can substitute this to equation number 1. Our equation number 1 is this one. We have determined this previously. And we can substitute volume of, we have this, these are similar terms. But this one, volume of sodium acetate is also equal to 1.20 volume of acetic acid. So this one is substituted here. So therefore, our new equation would then be volume of acetic acid plus 1.20 volume of acetic acid is equal to 0.1 liters. Finally, evaluating this expression, we get the value for the volume of acetic acid, and that is equal to 0.04545 liters, or is equal to 45.45 ml. Finally, since the total volume of the solution would then be 100 ml, then we can just calculate the volume of sodium acetate by subtracting 0.4545 to 100 ml. The resulting volume of sodium acetate would then be 54.55 ml. Okay, so these are the two ways to prepare a buffer solution. Okay, the third concept that I would like to teach you is the concept of buffer capacity. Buffer capacity is defined as the number of moles of an acid or base necessary to change the pH of the solution by 1 and divided by the pH change and the volume of the buffer in liters. So it has this following formula. So buffer capacity is represented by the Greek letter beta. So beta is equal to the mole of acid and the base over the absolute value of the pH change multiplied by the volume of the buffer in liters. So therefore, this equation can also be evaluated using this formula. MV, or molarity times volume of the acid or base, over the absolute value of the pH change multiplied by the volume of the buffer in liters, since mole is also equal to molarity times volume. Okay, suppose we have this example provided here. So what is the buffer capacity of a 50 ml hydrogen carbonate and carbonate buffer having a pH of 7.21, where in addition of 4 ml of 0.1 molar acetic hydrochloric acid changes the pH to 7.14. Okay, using this formula for the buffer capacity, all we need to do is just to substitute everything. So we have 0.1 molar, and that is the concentration of the acid, and the volume of the acid that is added in liters. So convert it to liters. 4 ml times the conversion factor 1 liter over 1000 ml, all over the pH change from 7.14 to 7.21 times the volume of the buffer in liters. So finally, we get this value, which is 0.11 moles of hydrochloric acid per liter of buffer. The next topic that I would like to discuss is about complex acid-base systems. When we talk about complex acid-base systems, we shall be talking about polyprotic acids, the titration curve of polyprotic acids, and finally, buffer preparation for polyprotic acids. What are polyprotic acids? Polyprotic acids are acids that have more than one ionizable hydrogen. Examples of polyprotic acids are the following. We have phosphoric acid, sulfuric acid, sulfurous acid, citric acid, and other organic acids. Okay, suppose the generic formula for a polyprotic acid is H3A. This is a triprotic acid. So since it has three ionizable hydrogen, and since it's also a weak acid, then it has these three equilibrium expressions. The first ionization of this triprotic acid is given in this first equation number 1. So H3A will yield H plus H2A minus. So in this case, we have this one is our acid and this one is its conjugate base. Okay, the second ionization is that of the conjugate base. The conjugate base in this context becomes the acid, which ionizes to hydrogen ion and Ha2 minus. So this one becomes the conjugate base. This species still has another ionizable hydrogen. So this can further ionize to Ha2 minus will produce another H plus and A3 minus, and that is the final ionization. So this one is the final conjugate base. Since all these equations are just partial ionization or reversible reactions, then there is an acid-base constant for each of these ionizations. So for the first ionization, we have Ka1 having this expression. Second ionization has Ka2, and third ionization has Ka3, having this expression, which is the molar concentration of the products or ionized products over the molar concentration of the unionized reactant. Okay, let's have a more specific example. Suppose we have phosphoric acid. Phosphoric acid is a weak acid and it has three ionizable hydrogen. So therefore it has three ionizations. The first ionization is we have phosphoric acid being ionized to hydrogen ion and dihydrogen phosphate ion. So this one becomes our weak acid and this one is conjugate base. Next, we have dihydrogen phosphate ion having two more ionizable hydrogens. So this one becomes weak acid and further ionizes to hydrogen ion and hydrogen phosphate ion. This one becomes our conjugate base. And finally, hydrogen phosphate ion has still one more ionizable hydrogen. So this one becomes a weak acid and further ionizes to hydrogen ion and phosphate ion. So that is the third and last ionization of phosphoric acid. The Ka values for these three ionizations are provided here. We have Ka1 that is equal to 7.2 times 10 to the negative 2, Ka2 6.2 times 10 to the negative 8, and Ka3 has 4.2 times 10 to the negative 13. Here are the expressions for the Ka1, Ka2, and Ka3 depending on the species that are formed during these individual ionizations. Okay, but how do we calculate the pH of polyprotic acids? Most often than not, the first ionization is the one that is being considered for the reason that the first ionization has the highest Ka value. So suppose the first ionization has 7.5 times 10 to the negative 2 Ka and the second ionization has 6.2 times 10 to the negative 8 and finally 10 to the negative 13 for the third ionization. So the succeeding ionizations has hydrogen ion that are relatively negligible compared to the hydrogen ion in the first ionization. So suppose we have a 1 molar phosphoric acid. 1 molar phosphoric acid can ionize to hydrogen ion at the first ionization. We have hydrogen ion at the second ionization and hydrogen ion at the third ionization. And the other species, hydrogen phosphate, and phosphate ions. Only the first ionization is considered to be significant in calculation of the pH. So that's why we only need to calculate the hydrogen ion in the first ionization if we are given a concentration of a polyprotic acid. So suppose we have phosphoric acid, 1 molar phosphoric acid. The first ionization would look like this. We have phosphoric acid would ionize to hydrogen ion and dihydrogen phosphate. So using the ice table, we can calculate the pH of this weak acid, weak polyprotic acid. So we have 1 for the I, we have 0 and 0. At the change, we have minus x, plus x, and plus x. And therefore, at equilibrium, we have 1 minus x molar, plus x molar, and plus x molar. Now we have this Ka expression, which is equal to x times x over 1 minus x is equal to 0.075. 0.075 is the value for the Ka1 or the equilibrium constant. So 7.5 times 10 to the negative 2 is just 0.075. Now we have to decide whether or not x is negligible. Okay, in order to decide whether or not x is negligible, we need to divide the initial concentration with that of the equilibrium constant value. So 1 divided by 0.075 is 13, and therefore x is not negligible. So we could not cancel x in this case. Therefore, we need to make use of a quadratic equation. So evaluating this expression, we get a quadratic equation that is equal to x squared plus 0.075x minus 0.075 is equal to 0. Using the quadratic formula after this, okay, you may use your calculator or you may use the online quadratic equation calculator. You can just search it in Google and you get the value of x, which is equal to 0.239, and that is the concentration of the hydrogen ion. So therefore we have 0.239 molar. Finally, we can calculate the concentration or the pH using this formula. pH is equal to negative log of hydrogen ion concentration, and finally the pH value would then be 0.621. Okay, how about for the second and the third ionization? So the second ionization is we have dihydrogen phosphate ion. So suppose you are asked to calculate the pH of 1 molar dihydrogen phosphate ion. So take note that the second ionization, this one, looks like this. Dihydrogen phosphate ionizes to H plus and hydrogen phosphate ion. So it has a Ka2 value. But also take note that dihydrogen phosphate is an ion that can undergo hydrolysis. So dihydrogen phosphate in equation number 2 reacts with water to form phosphoric acid and hydroxide ion. So therefore it can be both an acid and a base. Because of this, dihydrogen phosphate is what we call an amphiprotic species. So when we say amphiprotic, it is both an acid and a base. But how do we calculate the pH of an amphiprotic species? Okay, remember that the first ionization, this one, let's say it's A and this one is B. The first ionization produces dihydrogen phosphate, and dihydrogen phosphate produces hydrogen phosphate in the second ionization. So this one are just Ka1 and Ka2. But also take note that while the hydrogen phosphate produces hydrogen phosphate ion, this one, the hydrogen phosphate also produces phosphoric acid because of hydrolysis. So how do we reconcile this? One way to reconcile this is by deriving this expression. So suppose we have Ka1 times Ka2. So all we need to do here is just to multiply these two expressions. So the expression for Ka1 is H plus times dihydrogen phosphate ion over phosphoric acid. So this one is the Ka1 expression. This one. For Ka2 on the other hand, the expression would be this one. Okay, take note that both Ka1 and Ka2 has the same species, which is dihydrogen phosphate, so you can just cancel these two altogether. Okay, by the way, this one is the expressions and the values. So finally, we have this expression here. Ka1 times Ka2 is equal to hydrogen ion squared times hydrogen phosphate ion over phosphoric acid ion. But take note that these two are produced by the same dihydrogen phosphate ion. So this hydrogen phosphate, suppose, let's just color it hydrogen phosphate yellow, is produced by this one, this one. And similarly, we have phosphoric acid, this one, is produced from the same dihydrogen phosphate. So the source of these two species are the same. And take note that since the source is just the same and these species are just stoichiometrically equivalent, then we could say that the concentration of hydrogen phosphate ion is also equal to the concentration of phosphoric acid. So since their concentration are equal, then we can just cancel them out. Okay, so what happens afterwards? In the next slide, all that was left is just Ka1 times Ka2 is equal to hydrogen ion squared. Okay, in order to get the pH, we need to get the logarithm of these two, of this equality. So we get, take note that based on the rules on logarithmic functions, log of AB is equal to log of A plus log of B. And log of x raised to n is just equal to n log of x. So these are the rules for logarithmic functions. So what we get afterwards is just negative log of Ka1 plus negative log of Ka2 is equal to 2 negative log of hydrogen ion. Okay, but take note, negative log of Ka1 is just pKa1 and negative log of Ka2 is just pKa2. And we have 2, and furthermore we have negative log of hydrogen ion is just pH. So therefore pH is just equal to pKa1 plus pKa2 over 2. So irregardless of the concentration of the amphiprotic species, the pH is calculated like this. So the concentration of the amphiprotic species is not accounted for. So therefore, we can just calculate the pH to be, we have pKa1, negative log of Ka1 is, the Ka1 is 7.5 times 10 to the negative 2, and the Ka2 is negative log of 6.2 times 10 to the negative 8 all over 2. Okay, for this we have 1.12, 1.125 plus. For the other one we have 7.21 or 7.208 divided by 2. Okay, the answer is 4.17. Okay, so therefore the pH value for this amphiprotic species is 4.17. Okay, so that is also the same with the third ionization. Suppose you are asked to calculate the pH of 1 molar of sodium disodium hydrogen phosphate. Okay, disodium hydrogen phosphate is another amphiprotic species for the reason that when disodium hydrogen phosphate ionizes, it forms this one and this ion. And this ion can further ionize, and that is the third ionization of that polyprotic acid. We have hydrogen ion and phosphate ion which are formed. But take note that this can also undergo hydrolysis. So we have this one reacts with water to form dihydrogen phosphate and hydroxide. Okay, so take note, what are involved in this species or in this amphiprotic species is the third ionization and the second ionization. So this one is basically the third ionization, Ka3, and this species is from the second ionization, Ka2. So if we derive the same thing with that of the previous example, then we get a value for the pH which is equal to pKa2 plus pKa3 over 2. So irregardless of the value for the concentration of this amphiprotic species, we can just immediately calculate the pH value. So pKa2 is just 7.208 and pKa3 is negative log of negative log of 4.2 times 10 to the negative 13. Okay, the value is 12.38377 divided by 2. And therefore we can just calculate immediately the value for the pH. Okay, the value for the pH is 9.79. So once again, regardless of the concentration of the amphiprotic species, we can just immediately calculate the pH value using this formula. Okay, the third example would be about the third ionization. Okay, for the third ionization, we have, suppose you are asked to calculate the pH of 1 molar of sodium phosphate. Okay, sodium phosphate has ionizes into 3 sodium ion and phosphate ion. Okay, phosphate ion is the product of the third ionization. The third ionization looks like this: hydrogen ion and phosphate ion. And the Ka expression for that would be this expression. Okay, but take note that phosphate can undergo hydrolysis. So when it undergoes hydrolysis, it produces hydrogen phosphate ion and hydroxide. So therefore, what is only involved here is just Ka3, but phosphate is a conjugate base, so therefore we need to calculate the Kb value. So the Kb value can be calculated using this expression. Ka times Kb is equal to Kw. And therefore, Kb for phosphate is just equal to 1 times 10 to the negative 14 divided by the Ka value, which is equal to 4.2 times 10 to the negative 13. So therefore, the Kb value for the phosphate would be 0.0238. Okay, so since we now know the Kb value, we can just proceed with the ice table. Okay, the ice table would look like this. So we have 1 molar of phosphate, 0 and 0, minus x plus x plus x. And at equilibrium, we have 1 minus x molar, and x molar. So therefore, the Kb expression would then be x times x over 1 minus x. And that is equal to 0.0238. If we calculate whether or not x is negligible, x is not negligible. Okay, so suppose we have 1 molar divided by the Kb value, 0.0238, you get a value that would give you a hint that x is not negligible. Okay, the value is 42, and that is 10 to the 1. So therefore, x is not negligible. And we need to evaluate this expression using quadratic formula. Okay, transposing everything to the left side to get a quadratic formula having the form ax squared plus bx plus c is equal to 0. Then after that, we can calculate the quadratic formula or the root for the x using the quadratic formula or quadratic formula calculator. Okay, I'm just using the quadratic formula calculator here. So we have 1, 0.0238 and negative 0.0238. If you calculate the value for x, the value for x would then be x is equal to 0.143. And take note, x is equal to the concentration of the hydroxide. So now we can calculate the pOH value, which is negative log of 0.143. Okay. Therefore, the pOH value would be 0.85. Okay. Calculate the pH using by subtracting pOH to 14. We have 14 minus 0.85 is equal to 13.16 or 13.15. Therefore, the pH value for 1 molar sodium phosphate is 13.15. Okay, the next two topics that I would like to teach you is the titration curve for polyprotic acids. The titration curve for polyprotic acids looks like this. It has 3 equivalence points. So this red is one equivalence point, this one is another equivalence point, and this one is the last equivalence point. So we have equivalence of hydroxide added, meaning 1 mole of hydroxide will react with 1 ionization of a polyprotic acid, and so on and so forth. Okay, before the addition of hydroxide, most of the solution only has phosphoric acid. But upon addition of hydroxide, before the first equivalence point, some of the phosphoric acid are converted to dihydrogen phosphate, this one, dihydrogen phosphate, and some of the phosphoric acid that are not reacted. So in the first equivalence point, or prior to the first equivalence point, the predominating species are just dihydrogen phosphate and phosphoric acid. So this area or this region here is the buffer region for the first equivalence point. The buffer region is composed of the weak acid and its conjugate base. Okay, after the first equivalence point, or during at the first equivalence point, all the phosphoric acid are converted to dihydrogen phosphate. So all of these are already converted to that form. And as more moles of hydroxide are added, then this dihydrogen phosphate would be reacted further by hydroxide to produce hydrogen phosphate ion and water. So what is present after the first equivalence point are the species. We have dihydrogen phosphate, which is the one that is produced, and we have phosphate ion. We have hydrogen phosphate and dihydrogen phosphate. This region becomes another buffer region. So why is it a buffer region? For the reason that it is composed of the conjugate base and the weak acid of the conjugate base. Okay, when all of the dihydrogen phosphate are reacted with hydroxide, what is remained is only the hydrogen phosphate ion, and that is when we reach the third equivalence point, the second equivalence point. At the second equivalence point, all the dihydrogen phosphate are now converted to hydrogen phosphate. So all of this one is converted to that. If more equivalents or more moles of hydroxide are added after the second equivalence point, then hydrogen phosphate ion would still be reacted by hydroxide to form phosphate ion and water. Prior to the third equivalence point, the predominating species are now phosphate ion and hydrogen phosphate ion. So this becomes another buffer region. Okay, when all of the equivalents of hydrogen phosphate is one, when all of the hydrogens of hydrogen phosphate are reacted by hydroxide ion, then that is when we form the last product, which is phosphate ion. Okay, so phosphoric acid has three ionizable hydrogen and therefore three equivalence points. And at the middle of each equivalence points are buffer regions. So we have this buffer region number 1, this buffer region number 2, and this buffer region number 3. And also take note that when the concentration of the weak acid is equal to the concentration of the conjugate base, then the pH would then be equal to the pKa. And that is the concentration wherein the buffer capacity is the strongest. So the strongest buffer capacity are the midpoint of each buffer region, and that is when, once again, the weak acid concentration is equal to that of the conjugate base concentration. The weak acid concentration is equal to the conjugate base concentration. Okay, so how about when you prepare a buffer solution using a polyprotic acid? We can still follow the previous calculations from buffer preparation and apply it for polyprotic acids. So for example, if you are asked here, prepare a 100 ml pH 8 phosphate buffer from 1 molar sodium dihydrogen phosphate and 1 molar disodium hydrogen phosphate. So take note that if you are asked to prepare a pH 8 phosphate buffer, then you need to choose the species that are nearest to it or nearest to the pKa of that species. So for example, the pKa2 of phosphoric acid is 7.21, whereas the pKa1 is, I think this one is 1.12 and not 2.12. So the pKa1 is 1.12. So in order to prepare a pH 8 phosphate buffer, then you need to pick the pKa value that is nearest to that pH and the species that are present in that pKa value. So suppose we want to prepare a pH 8 phosphate buffer, so the nearest to 8 is 7.21, and that is pKa2. So 7.21 pKa2 is the second ionization, and the species of the second ionization is hydrogen phosphate ion and dihydrogen phosphate ion. So therefore, we need to pick those two species and identify which of those is the conjugate base and the weak acid. So from this problem, we know that the volume of the acid plus the volume of the conjugate base is equal to 100 ml. And since we are using the pKa2 or the second ionization, so we need to make use of the pKa2 value and plug it into the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation would look like this. pH is equal to pKa2 plus log of the conjugate base concentration over the weak acid concentration. So we can further evaluate this expression by supplying the concentration of the conjugate base and the weak acid. So the concentration of the conjugate base is, we have 1 molar times the volume of the conjugate base over the total volume, and we also have 1 molar volume of the acid times the volume of the acid over the total volume. We cancel the same units, we have Vt, and we can further evaluate this expression to um, the next expression. So we have pH is equal to pKa2 plus log of V conjugate base over V weak acid. So supplying the values for the pH and pKa, then we have pH of 8 and pKa is 7.21. 7.21 is this one, plus log of the volume of conjugate base over volume of weak acid. So transpose this one to the other side, and we get 8 minus 7.21 is equal to log of V conjugate base over V of acid. Take the antilog to remove the logarithmic function, and you get specific value for the antilog of 0.79. Okay, so evaluating this expression further, we get V of conjugate base is equal to 6.17 V of acid. Okay. Evaluating the antilog of 0.79, we get 6.17, and the logarithmic function is removed. So 6.17 is equal to V of conjugate base over V of acid. And further evaluating this expression, we get V of conjugate base is equal to 6.17 V of acid. Okay, taking the first equation we've had, this one, equation number 1, and substituting V of conjugate base to it, we have V of acid plus V of conjugate base. Our volume of conjugate base is equal to 100 ml. And substituting this 6.17 V of acid here, we get V of acid, volume of acid plus 6.17 volume of acid is equal to 100 ml. We get 7.17 volume of acid is equal to 100 ml. Divide both sides by 7.17 and we get a value that is equal to 13.95, which ml, which should be the volume of acid that should be added to 86.05 ml of the volume of the conjugate base. Okay, so this is how you prepare a buffer from polyprotic acids. Okay, so if you are asked to prepare a pH 3 buffer or pH 2 buffer, then you need to make use of the first this species, because this one is the nearest. So we have phosphoric acid and dihydrogen phosphate ion should be mixed. And if you want to prepare a pH 12 buffer, then you need to make use of hydrogen phosphate ion and phosphate ion. Okay, the calculation is still the same with this one. Okay, so this is the end of our lesson for acid-base equilibria.